Here is the presentation for our work on generalized category discovery, named SSR squared GCD. Generalized category discovery, or GCD, is an open set recognition problem. In GCD, we have labeled data from known classes and unlabeled data mixed with known and novel classes. The goal of GCD is to categorize unlabeled data. Recently, multi-modal GCD methods leverage information occurs from the textual modality to facilitate knowledge transfer between old and new classes. These methods use vision language models such as CLIP to generate text for visual data. However, they have some limitations. First, the widely used semi-supervised contrastive losses in GCD leads to imbalanced compression. That is, representations of known classes are overcompressed, while those of novel classes lack supervision signals and thus remain undercompressed. Besides, some multimodal GCD methods overemphasized inter-modal alignment while ignoring inter-modal structure of learned representations. So in this paper, we propose a unified framework with two core components. To generate high-quality initial text representations, we first retrieve top-K similar text and attributes from the prompts, then aggregate them with adaptive weights. This strategy, named RTA, enriches semantic information of generated representations. The core of our framework is the semi-supervised rate reduction objective, derived from the principle of maximal coding rate reduction to learn structured representations. Here, the loss consists of three terms. First, the total coding rate term to globally expand all embeddings. Second, the supervised compression term to compress embeddings of labeled samples. And the self-supervised compression term that uses pseudo-labels to compress embeddings of unlabeled samples. To effectively train our framework, we deploy dual-branch classifiers to produce pseudo-labels and adopt a two-stage training pipeline. During the warm-up stage, we use supervised rate reduction to stabilize the representation learning and cluster the learned representations from each modality. During the alignment stage, we apply the full SSR squared loss and additional co-tint loss to align classifiers' predictions between the visual and textual modalities. This strategy prevents early pseudo-label mistakes from misleading the optimization of the self-supervised compression term. Finally, we evaluate our method on 8 generic and fine-grained datasets. Our method reduces the rank gap between known and novel classes, avoiding imbalanced compression. For representation learning, overemphasizing intermodal alignment may result in intra-modal misalignment. By contrast, our proposed SSR squared objective encourages intra-modal alignment while not harming the intermodal alignment. This is because the downstream clustering algorithms is built on the assumption that the intra-modal embeddings of augmented data pairs should be close enough to be assigned to the same cluster. Owing to this, our method outperforms GCD counterparts on 7 benchmarks. Thanks for your listening.